Okay, I've got what I consider to be an interesting initial value problem up here on the board. Y prime is this piecewise function. So if y is less than 4, y prime is just negative 2y. But if y is bigger than 4, it's negative 2y plus 3. So essentially at time 4, we added a 3 to the derivative. So this creates this function that is not differentiable at 4. So you'll notice there's no equality here. If y is 4, it's not going to be differentiable. Okay. You might think, well, she's just coming up with weird problems to torture us. But this could show up in a real-world situation. I could have something like this describing an electric circuit. There's an example in your text with an RC circuit that's very similar to this, except that what they turn on at their time, instead of being just a constant function, is an exponentially decaying function. But this would be like I have this electric circuit, and at time 4, I suddenly add an external voltage source. I add a steady source of 3 volts to the system. Okay. And when we have something like that, even though our function is not differentiable there, generally speaking, we're looking for a continuous function. Remember, a function can be continuous but not differentiable if it has a sudden change, a corner, a cusp, something like that, but the function itself doesn't jump, it just has a radical change in its behavior. And generally, when we're working with differential equations like this, that's the sort of thing we're going to be looking for. So we're going to suppose that our solution y will be a continuous function, it just won't be differentiable. And I'm going to rewrite this as y prime is equal to negative 2y plus 3 times mu sub 4 of t. So this is turning on at time 4, 3, so that I'm adding that to my y prime. Now, technically, this equation defines a value of y prime at time 4, and I know that the function is not differentiable at time 4. However, it turns out that's an ignorable problem. This models the situation very nicely. I know, because I've got this piecewise function for the derivative, to expect a sudden change at 4, so to expect it to not be differentiable at 4, and we'll see that we sort of get a piecewise function as well for our solution, so that that will reflect that sudden change. Okay. So this formula would be valid except at 4, because there is no value of y prime at 4. Okay. But now I can use Laplace transforms to try to solve this. And this is something that we could not do. Well, I guess I could solve this equation and then this equation separately, but now I can solve them all at once without having to treat it as 2 separate problems. Okay. So I've written up here the formulas that we're going to be using. Just one note on that. In the formula sheet, the formulas are given in a slightly different form, because there's sort of a column for y of t and then another column for capital Y of s. I'm choosing to write them as an equation. The Laplace transform of this equals that. That's actually just to save space so that I don't have to write the headings of the column here. But what that means is that what I'm writing on the board, even though it's exactly equivalent to what's on your formula sheet, isn't an exact match to the way it's written on the formula sheet. So again, I just want to encourage you, anytime you're watching videos in Chapter 6, to have that formula sheet with you so that you get comfortable with the way I'm writing it here, the way it's written on the formula sheet, and you can see those equivalences, and you're not sitting there saying, wait, that's not exactly what it says on my piece of paper. It's exactly equivalent to what it says on your piece of paper. Okay, excellent. So let us take the Laplace transform of both sides. I think what I'm going to do is start over here, fill this up, and then I can move over there. So the Laplace transform of y prime is going to equal the Laplace transform of negative 2y plus 3 mu sub 4 of t. Now, for the Laplace transform of y prime, I can use rule number 11. That's just going to be s copies of the Laplace transform of y minus my initial condition, and I was told that that was equal to 5. Okay. So I get this by using rule 11. And now here, I'm just going to use the fact that the Laplace transform is linear. So I'm going to break this up. I'm going to say this is negative 2 times the Laplace transform at y plus 3 times the Laplace transform of this Heaviside function. Okay. So that's just using linearity. All right, now I'm taking the Laplace transform of the Heaviside function. That was formula 5 up here. So I can say S times the Laplace transform at y minus 5 is 2 times the Laplace transform of y plus 3 times, now here my A is 4, so I'm going to get e to the negative 4s over s. Okay, excellent. So now I've taken the Laplace transform of both sides. So I've converted from this differential equation that has a derivative in it to this algebraic equation that just has this unknown function being multiplied and added, and just algebra stuff is being done to it. All right, so I'm going to add the 5 over to this side and subtract the 2 Laplace oh, was this a negative 2? That was a negative 2. So I'm going to add the 2 copies of the Laplace transform of y over to this other side. So I'm going to get s times the Laplace transform of y plus 2 times the Laplace transform of y is going to equal 5, because I'll add that over, plus 3 copies of e to the negative 4s all over s. Okay, let me clear some space. So now I can factor out the Laplace transform of y. So that's being multiplied by s plus 2, and that's equal to 5 plus 3 e to the negative 4s all over s. So I'm going to divide both sides by s plus 2. So the Laplace transform of y is going to be 5 over s plus 2 plus 3 e to the negative 4s over s times s plus 2. Excellent. So we've found our function that's the Laplace transform of y. I want to be able to now take the inverse transform. So I like the way this piece looks, because that looks like the right-hand side here. Well, 5 copies of it. So I'll be able to use rule 1. This piece I think I'm going to want to rewrite. Okay. So probably I'm going to want to rewrite that as 3e to the negative 4s times 1 over s times s plus 2. Looks like that's going to be setting me up to use rule number 14. 3 is just a constant, but I'm multiplying something by e to the negative 4s, so I'm hoping this is the Laplace transform of something, and then that something I'm going to translate and multiply by the Heaviside function. Now, I'm going to just do some side work to work with this piece right here, because I don't like having a fraction with 2 factors on the bottom. I want to use partial fractions to get it to be 2 pieces that look like that. So I'm going to say 1 over s times s plus 2. That's 2 linear factors. So that's going to be 2 fractions whose denominators are s and s plus 2. The numerators will just be constants, so just a and b. So now I would multiply through by s times s plus 2 to clear the denominators. So I get 1 is equal to a times s plus 2 plus b times s. Convenient numbers to plug in would be if s equals negative 2. That's going to give me 1 equals negative 2b, and so b is negative 1/2. If s is equal to 0, that'll kill off the b's. That gives me 1 is equal to 2a, and so a is positive 1/2. So I can now plug that in. I can say the Laplace transform of y, that's the original function that I was looking for, is 5 over s plus 2 plus 3e to the negative 4s times, let's see, a was 1/2, so 1/2 over s minus 1/2 over s plus 2. Excellent. So now I've got the pieces set up so that hopefully they're going to match these formulas kind of nicely. So I can apply the inverse Laplace transform to each side. So when I do that, I'm going to get y of t, that was the original function of t that I was looking for, is going to be, I'm going to just use the fact that the Laplace transform is linear, so I can say that's going to be 5 copies of the inverse Laplace transform of 1 over s plus 2, plus 3 copies of the inverse Laplace transform of e to the negative 4s times 1/2 over s minus 1/2 over s plus 2. And I can see this piece is going to be the trickier piece. Let's go ahead and get this piece. That's going to give me 5 copies of, this is a match for this if my a is negative 2. So I'm going to just get e to the negative 2t. Okay. Plus I'm going to get 3 copies of this. Now I've got the e to the negative 4s times this. So I'm thinking of this as the Laplace transform of some function f. I'm going to just write f instead of y, because y I was using for the entire thing. F I'm going to be using just for this piece. So if that's the Laplace transform of f, let's see if we can't figure out what f is. Okay, so f would be 1/2 the inverse Laplace transform of 1 over s, which is what I would get here if a is 0. So that would be e to the 0t, which is just 1, minus 1/2 the inverse Laplace transform of 1 over s plus 2, which is what I get if a is negative 2, so e to the negative 2t. So that's my f. I can see here my a, now not the a from this formula, the a from formula 14. A is 4. Okay. So I can now say that this piece, that's going to be, I'm just going to write it down here, 3 copies of, when I have an exponential function times a Laplace transform, I'm getting the heavy side function. So this will be mu sub 4 of t times, now I'm going to have the function that this was the Laplace transform of my function f, but instead of evaluated at t, it's going to be evaluated at t minus a. So in this case at t minus 4. So I'm going to get 1/2 minus 1/2 e to the negative 2 times t minus 4. So let's just write out our final answer, fitting it onto one line. My y of t is this piece, 5 e to the negative 2t, plus 3 copies of the heavy side function, multiplied by 1/2 minus 1/2 e to the negative 2 times t minus 4. And you can see, because we've got this heavy side function here, that's what's going to introduce the fact that my function will not be differentiable at time 4.